Hi, I'm Lazar, and I'll talk about dynamic matchings under Vertex updates. This is a joint work with Hung, Shay, and Virginia. This work concerns graph matching, which is a fundamental problem and has been extensively studied. Matching is simply a set of disjoint edges. Throughout this talk, I'll use n to denote the number of vertices in the graph and KLM to denote the matching. We'll be interested in maximum cardinality matching, or MCM, which is a matching of maximum possible size. The main focus of this talk is maximal matching, or MM, which is a matching to which we cannot add any edge. It is well known that maximal matching is a tool approximation to MCM. And besides MM, which is the main focus of this talk, we'll also be interested in better than two approximate MCM. We study matching algorithms in dynamic setting. In the standard dynamic setting, with edge updates, there are many results. This is to be contrasted with the setting with vertex updates, where the literature is very sparse. In addition, the algorithms work either in the incremental setting, where we have vertex insertions, or the decremental setting, where the vertices leave the graph. There are only a few results in the context of vertex updates, and none of them is for fully dynamic graphs, where we have both insertions and deletions intertwined. This work initiates the study of fully dynamic matching algorithms under vertex updates. Let's see an example of a fully dynamic algorithm for maintaining a maximal matching in the standard setting with edge updates. We have a sequence of updates, and the current state of the graph is denoted by GI. Here, TI denotes the update time, which is the time it takes for the algorithm to update the matching. There are two notions of update time. The first one is worst case update time, which is maximum of TI. And the second one is amortized update time, which is average TI. There are several results for dynamic maximal matching. There is a naive deterministic algorithm which spends linear time following every update, and the state of the art is square root of m by Neyman and Solomon. In the context of randomized algorithms, PSG showed how to maintain a maximal matching in O of log n time, which was subsequently improved by Solomon to a constant update time. There are also results for bounded arboricity graphs. Arboricity of a given graph G is the minimum number of forests required to decompose G. And this is a parameter that ranges from 1 to square root of m. Note that the state-of-the-art deterministic algorithm for general graphs has polynomial update time. Another problem of interest is a better than 2 MCM. We have several deterministic algorithms with different trade-offs. There are randomized algorithms for general graphs and also for bipartite graphs under adaptive adversaries. For the restricted graph families, we have several results for bounded arboricity graphs. There is also a trade-off for bounded degree graphs. And our recent result gives a 1 plus epsilon approximation for the graphs of bounded neighborhood independence. This parameter is equal to the size of largest independent set in the neighborhood of any vertex. There are also 1 plus epsilon approximate algorithms for incremental and decremental setting. As it is the case for MM, the state of the art for deterministic better than 2 approximate MCM is polynomial update time. We now switch our focus to dynamic matchings under vertex updates. Here we see an example of algorithm which maintains a maximal matching. And again, we use GI to denote the state of the graph following each update, and TI to denote the ith update time. Here, the notion of worst case update time remains as before, but the definition of amortized update time is different. It is now the total runtime divided by the overall number of edges inserted to or deleted from the graph. One notion that we'll be interested in is the recourse bound. This is the number of changes to the matching per update step. And similarly to the update time, the bound on the recourse can be either worst case or amortized. We'll be particularly interested in the worst case bound. There is a recent theorem which says that for any gamma, t, and epsilon, any gamma approximate MCM algorithm with update time t can be transformed as a black box to another algorithm, which has a slightly worse approximation guarantee and update time, but has a worst case bound on the recourse of 1 over epsilon. This theorem applies to both settings, edge and vertex updates. We now present the previous results on matching under vertex updates. All the results concern bipartite graphs where one side is fixed and the other side dynamically changes. In the incremental model, the vertices or clients appear dynamically together with their neighboring edges. The other version is decremental. There we have clients leaving the graph following each update. As I mentioned before, the previous results either apply to incremental or the decremental setting. In particular, Bozek et al. Gave an algorithm which runs in O of m square root of n time, has an amortized recourse of O square root of n, and it applies to either incremental or the decremental setting. There is also 1 plus epsilon approximates MCM with an amortized recourse of 1 over epsilon, also for either incremental or decremental setting. And finally, there is exact MCM algorithm with an amortized recourse of log squared of n, and it applies to incremental setting. Note that all these results, for all of these results, we can get a worst case recourse bound of 1 over epsilon by applying the theorem of SS21. For the first and the third result, the matching is no longer exact, but for the second result, we get the same approximation with the same runtime. This work draws connections between dynamic graph algorithms and the online algorithms. To understand the connections, let's first see the main goals of each of the areas. For dynamic graph algorithms, we usually consider edge updates, whereas in the online algorithms, we usually consider vertex updates and the graphs are incremental. The main optimization criterion in the dynamic algorithms is update time, whereas in the online algorithms, the main criterion is the competitive ratio. Finally, we can revoke the decisions in dynamic algorithms, whereas the decisions in the online algorithms are usually irrevocable. Previous results on dynamic matchings and the vertex updates were inspired by online algorithms, and as I mentioned before, they are either incremental or decremental. This paper initiates the study of fully dynamic matchings under vertex updates. I'll now summarize our main results. The first observation concerns what we call the basic dynamic setting, where we have a bipartite graph with one side fixed. The vertices on the other side undergo both insertions and deletions. Here, we observe that there is a simple maximal matching algorithm with a constant amortized update time. In addition, this algorithm never removes an edge from the matching, and we call such an algorithm irrevocable. We note that irrevocable algorithm for maximal matching implies that the worst case bound on the recourse is constant. We also give a lower bound for what we call the medium dynamic setting. In this setting, we have a bipartite graphs with both sides dynamically changing. Our lower bound says that an irrevocable algorithm with a runtime of n to the 1 minus eta for any fixed eta would refute the OMV conjecture. And also the update time of m to the eta for some fixed eta would refute the triangle detection conjecture. Next, we consider the setting which we denote by medium decremental. In this setting, we have a bipartite graphs where the vertices on both sides can leave the graph. With a couple of more technical insights, we can show that the same bound applies to medium decremental setting, which is more restricted. So what we get here is in fact a stronger lower bound. In order for it to hold in the decremental setting, we have to assume either that the initial matching is fixed or that the sequence of deletions is preceded by a batch of insertions. It would be interesting to see if the same lower bound applies without making these assumptions. We contrast this polynomial lower bound on the update time for irrevocable algorithms with a constant upper bound for one-revocable algorithms. In fact, our upper bound applies to a more general setting, which we call general dynamic, where we have general graphs and the vertices can both be inserted to or deleted and deleted from the graph. We present a maximal matching algorithm for this setting, which has a constant amortized update time. In addition, this algorithm is one-revocable, which means that it can remove at most one edge from the maintained matching. Here we distinguish between removals caused by the algorithm and what we call deletions of a matched edge, which are performed by the adversary. We also know that the one-revocable algorithm implies a bound of O of I on the recourse. These two results tell us that the revocability is the pivotal measure of maximal matching under vertex updates. On one hand, we cannot have an efficient algorithm, even for decremental bipartite graphs, due to the above lower bound. And on the other hand, we can have an algorithm which is one-revocable and has a constant update time. Finally, we switch our attention back to the basic dynamic setting and show an algorithm which maintains an E over E minus 1 approximate MCM in constant update time. This algorithm builds on the online ranking algorithm by KVV. We also note that one can get the worst case bound of O of 1 over epsilon on the recourse while losing slightly in the approximation guarantee and the update time. The first takeaway message is that revocability is a more refined measure of recourse. In particular, we show that it is a pivotal measure of maximal matching algorithms, maximal matching algorithms. We can get an efficient one-revocable algorithm with a constant update time, whereas irrevocable algorithm requires a linear update time. As I said, this is a more refined measure of recourse. In particular, an i-revocable maximal matching algorithm implies a bound of O of I on its recourse. We also study better than two approximate MCM problem. In general graphs, it is still a major open problem to get a better than two approximation is some polynomial update time under edge updates. And on the other hand, we gave a constant time algorithm for maintaining a better than two approximate MCM under vertex updates. This algorithm builds on the online ranking algorithm of KVV90. This work draws connections between online and dynamic algorithms. In particular, our approximate MCM builds heavily on the online algorithm of KVV, and the revocability parameter that we use is inspired by irrevocability restrictions underlying online algorithms. We hope that a further study of these two areas together, rather than independently, will strengthen these connections and unveil new ones, and we anticipate that ultimately this will also advance the state of the art in online algorithms. In this talk, I will only go over our result on one-revocable maximal matching. The first algorithm that we present has a high bound on the recourse, but it contains the main ideas behind the one-revocable algorithm. And then I'll show the insights required to achieve the one-revocability. I'll start with the main intuition behind the algorithm. An assumption that we use is that the sequence of updates start from an empty graph. Whenever a vertex U gets inserted in the graph, the algorithm gets theta of Degoview credits. The interesting case is when a matched vertex U gets deleted from the graph. For that case, we observe that the amount of credits that the algorithm obtains is the minimum of the degrees of its endpoints. And the guiding principle behind our algorithm is that every edge UV in the matching can borrow mean Degoview credits from the neighbor that creates it. Such a neighbor obtained these credits upon its insertion into the graph. Let's start with some definitions. For each vertex in the graph, we maintain a constant factor estimation of its degree, denoted by deg prime. we partition the vertex set into risky vertices comprised of all the free vertices and all the matched vertices with estimated degree larger by a factor of 2 than their mates degree, and the safe vertices, which are the matched vertices with estimated degree smaller than twice the degree of their mates. From the definition, it follows that each matched edge contains at most one point that is risky. The intuition behind the names is that safe vertices have enough of credits for scanning their entire neighborhoods when they become free, whereas risky vertices might not have, and we have to use some workarounds. For each vertex U in the graph, we maintain a partition of its neighbors into safe and risky ones. The risky set is further partitioned into risky of estimated degree at most deg prime of U, and the ones of higher estimated degree. The key invariant that this algorithm maintains is that for each risky vertex, all its free neighbors have their estimated degree no greater than deg prime of U. We now dive into the details of the algorithm. First, we explain the easier case in which we handle a safe vertex. In this case, we have deg of U credits, so this treatment should be trivial. The main challenge here is to maintain all the data structures together with invariant 1, which is crucial for handling risky vertices. As I mentioned earlier, a risky vertex might not have enough of credits to scan its entire neighborhood. First, the algorithm scans the risky neighborhood of larger estimated degree and looks for a free vertex. If such a free neighbor has been found, we match it to U. Whenever some vertex changes from safe to risky and vice versa, we update its neighbors about this change in time linear in its degree. Overall, this takes O of deg of U time. Next, if the set of neighbors of smaller estimated degree is empty, U informs its neighbors that it became free and thus risky. The total cost of this part is O of deg of U, and the invariant 1 is maintained. Finally, if the set of neighbors of smaller estimated degree is non-empty, we have to take some extra steps in order to maintain the invariant. First, we take an arbitrary vertex W and match it to U, while maintaining the data structures of all the affected neighbors. Finally, we handle the old mate of W, which is W prime, recursively. Ignoring the recursive call, the total update time of this part is again O of deg of U, and the invariant 1 is maintained since U got matched. Overall, the total update time of the first level of recursion is O of deg of U. By the properties of risky and safe vertices, we know that W prime has degree smaller by a factor of 2 than degree of U, and this allows us to bound the total update time by a geometric sum, which evaluates to O of deg of U. To argue the correctness of the algorithm, we observe that U is left free only if it had no free vertices in its risky neighborhood. We know that all its safe neighbors are matched, and the maximality follows. It remains to show how to handle a risky vertex, which is perhaps the most interesting part of the update algorithm. Due to invariant 1, we know that all its free neighbors, if it has any, have no greater estimated degree. If the set of these vertices is empty, we leave U unmatched. Otherwise, if it's non-empty, we take an arbitrary neighbor W. If W was previously matched, we remove this edge from M and add UW to the matching, and the vertex W, which is the old mate of the vertex W prime, which is the old mate of W. This vertex is a safe vertex that became free. In order to maintain the data structure and invariant 1, we invoke handle safe on W prime. The total time this procedure takes, ignoring the call to handle safe, is proportional to degree of W. From the previous case, we know that handle safe also takes time proportional to degree of W. Note that U is a risky vertex, and we might not have enough of credits assigned to it. As a result, we will charge the cost of this procedure, which is O of degree of W, to the creation of the new matched new matching edge, UW. This is in check since every matched edge can be charged a cost proportional to the minimum of degrees of its endpoints. Another key point here is that edge WW prime might have been previously charged with some costs, but this cost is proportional to the minimum of the degrees of its endpoints, which is degree of W prime. By the properties of risky and safe vertices, we know that W prime has degree less than degree of W by a factor of at least 2, which allows us to bound the total cost assigned to UW by a geometric sum which evaluates to O of degree of W as required. To argue the correctness of this procedure, we recall that U is left free only if the sets R at most U is empty. And from invariant 1, it follows that U does not have any free neighbors, which means that the matching is maximal. We now summarize the charging scheme of the algorithm. When a vertex gets inserted, it gets handled as a safe vertex, and the algorithm has credits for that. The interesting case is when a vertex becomes free due to its neighbor's deletion. Such a vertex U was either safe and the deletion provides us with enough of credits, or it was risky and we charge the cost to a newly created edge. This concludes the description of our highly revocable algorithm. We now proceed to explain the ingredients required for obtaining a one-revocable maximal matching algorithm. First of all, we define a new set of vertices, which we call the outliers. These are the safe vertices that became free. The guiding principle behind this modified algorithm is that a safe vertex never removes any edge from M, whereas a risky vertex might remove but at most one. The new invariant which we would like to maintain is that every risky vertex has all its free neighbors either in the set of outliers or in the set of risky vertices of no larger estimated degree. The procedure for handling safe vertices is as follows. We look for a free neighbor and match it to U while maintaining the data structures. If such a neighbor doesn't exist, we mark U as an outlier and update its neighbors. The key point here is that while handling a safe vertex, we do not remove any edge from M. If U cannot be matched, we instead mark it as an outlier so as to maintain the invariant 1 prime. To handle a risky vertex, we distinguish two cases. First, if the set of outliers is non-empty, we take an arbitrary vertex from there and match it to U. Here we recall that all the outliers are free. Otherwise, we handle U as in the highly revocable case. This treatment might render some vertex W prime free. We know that this vertex is safe since it was matched to a previously risky vertex. As we have seen, handle safe does not remove edges from M. This allows us to conclude that the algorithm performs at most one removal per update step. We have thus shown how to maintain a one revocable maximal matching efficiently. Note that the amortized update time of our algorithm is constant. Indeed, the charging scheme that we saw handles any update within time linear in the number of credits obtained from a single vertex update that is assigned uniquely to it. To summarize, this work initiates the study of matching algorithms under fully dynamic vertex updates. Our main focus is on maximal matching. First, we observe that there is a simple irrevocable algorithm with constant update time in bipartite graphs where one side is fixed and the other side is fully dynamic. Second, we show polynomial amortized lower bounds on the update time for irrevocable algorithms in the medium dynamic setting where both sides dynamically change. These lower bounds hold under the OMV and triangle detection conjecture. In contrast to these lower bounds, we present a one revocable algorithm with constant amortized update time, which applies even to non-bipartite graphs. It works in the general dynamic setting. Our findings identify the revocability as a pivotal measure for maximal matching algorithms. In particular, this measure is more refined than the recourse bound. For better than 2 approximations, we can get a 1 minus 1 over e approximate algorithm for bipartite graphs where one side is fixed and the other dynamically changes. This algorithm relies heavily on the classic online ranking algorithm of KVV. More specifically, we show that the KVV matching can be maintained dynamically under arrivals and departures of clients with constant amortized update time. In the standard setting of edge updates, getting even a subpolynomial update time is a major open problem. It would be interesting to see if we can get anything for a setting between the standard one of edge updates and the basic dynamic setting of vertex updates, such as the medium dynamic setting where both sides can change dynamically. In this work, we demonstrate how the insights from the area of online algorithms can be used to advance dynamic graph algorithms. Despite the inherent connections between these two areas of algorithms, they have been studied almost always independently of each other. We anticipate that a thorough study of these two areas together, rather than separately, will contribute significantly to both.